Thanks, everyone. Yeah, so just for folks in the room who I haven't had the chance to interact with in the consortium, my name is Joe Negri. I'm a product manager here at Benchling, and I'm going to talk today about our work in the last year plus building converters for ASM. So software that will take instrument outputs and generate the ASM based off the models that have been published by Allotrope. So make sure everything will advance. All right. So I guess now having spent a fair bit of time sort of working on this, I sort of break down this process of building a converter into kind of three steps. The first being sort of refine the ASM model, which is mostly done through the working groups. And I won't focus so much on this initially, but if time allows, I'll come back to it at the end. But I do want to call out the define, redefine, because while I think in some of the talks already today, there has been discussions around really the maturity of the ontology. And as we just sort of saw in the last talk, when you sort of actually empirically compare the ontology to other ontologies, it is quite immature. I think actually the ASM themselves, an instantiation of these ontologies into a data model, we often actually find when we sort of actually apply this to sort of real instruments and real data, there's sort of more work to be done. And so it's not a critique of the ASM, but it's just more, I think, kind of a call out to the community that there's still work to be done here. So I'll come back to that later. And then the next really step in the process is defining that mapping of, how do you go from, what the instrument output of, say, the respective technique to the corresponding ASM. And this work is largely done with subject matter expertise who have to have sort of knowledge of the technique itself, as well as some knowledge of the ASM, which actually finding those two things is not always easy. And then lastly, you need software engineers with the ability to actually develop the code to now actually write the code to execute the conversion between the two. And if you get through all these things, you realize the benefits at the end. And so there, it is actually very beneficial, but you have to sort of make sure that you can kind of go through these steps. So, and I think kind of on reflecting on this, there's sort of questions about why has this been, what makes this challenging? And so I think one thing as we sort of call out, while there's familiarity with allotrope and the ontology and the ASM in some places, actually getting sort of all of the necessary parties together to actually build tools leveraging this, requires sort of a cross-disciplinary team that has very specialized knowledge. Like I said, folks who sort of have deep knowledge of the techniques, but also deep knowledge of data modeling and specifically deep knowledge of ASM and AFO can be hard to get. And then obviously the building the actual converters, some of the instrument outputs is quite tricky because, as I think anyone who's tried to do this knows, that not all instruments make this very easy. So and then I think, in terms of there's a sort of the confidence in what you've built. Do you have sufficient data and documentation to ensure that the model that you're building is actually representative of the technique? And then for any piece of software that you're then writing to do this conversion, if you sort of accounted for the variability that any, say, one vendor actually outputs. And then I think lastly, and a colleague said this recently, and for me, it actually really kind of summed up what makes this tricky, is that you're converting from something you have no control over, which is whatever the output for the instrument is, to something you only have some control over, which is the ASM format. And so when you kind of are you're between sort of a hard place and a semi-hard place. And so it actually makes the work of doing this kind of tricky at times. So I want to sort of get into how have we been doing on this? And I actually like to think I think we've been doing really well, and I think we're actually starting to actually build momentum in this area as well. So in last September, we launched Allotropy as an open source library of ASM converters. I'm referring to them as converters in this talk because I want to be clear, we're converting to ASM. Within the project, we typically refer to these as parsers or adapters. So forgive me if my talk is not semantically correct. But since then, we've actually doubled the number that we have, and we are continuously adding more. And we now have adapters and converters representing 8 of the ASMs. And so, this is a screenshot from our README page where we're sort of keeping this tally, and I'm hoping that very soon this is going to get long enough that it won't fit onto a single slide. And the QR code here will bring you to the site. Um, so in terms of, what were some of the strategies we've tried to adopt to actually help with this mapping? Um, and one of these is actually trying to sort of build a pattern, repeat on it. And so what we've been trying to do is basically trying to create, what is the sort of defined packet of requirements to do this? And um, this is sort of important because one, the individual that you might be working with might have knowledge of the technique, they might have knowledge of the ASM, they might have neither, but are a software engineer. And so it's sort of giving them all the pieces that they need to connect the dots. And so what we try to do as a sort of a representative pattern of this is say, okay, what is the data model we're trying to target? Um, and give sort of a plain language description of the mapping. This goes here, this means that. Because as we know, while ontologies are semantically correct, they are not always directly comprehensible. And so we also try to put together sort of a minimum worked example of say, this is sort of what we expect the JSON to look at, and also define what we expect the input to be. And we have to very often sort of say, this is sort of the, you know, these things need to have specifications. You have to say, we expect this format from this instrument. And that might not be all the formats that instrument produces. And then actually taking this one step further and actually trying to create templates of this. And so having a pre-configured template for each of the ASM schemas that we're trying to target. And what this does is it then allows a new SME who maybe has familiarity with the technique, but less familiarity with, say, the ASM, to sort of pattern match off an existing requirement and say, oh, okay, well, I know what this maps to, without them necessarily having to say, read the code to know exactly what the behavior is. And this also helps kind of ensure consistency across these. And in both of these things, we've actually have now started adding to the repo. So you can go into the repo and look at what were the requirements for one of these adapters or converters. Um, I think a few of the lessons that we've learned in just on this side of sort of the data mapping side, one is that the ASM schema sort of operate more as a framework than a specification. And that might be a feature, not a bug. I don't. I think that might be something for a kind of broader discussion. But I think there's one thing where it's just like we have fields that are defined in the ontology, like sample identifier. But when you're actually trying to map this out instrument data, what should that be? Should that be what the instrument says a sample identifier? If really what that is a written name? These are the sorts of kind of ambiguities that can kind of creep in here. And then seemingly other fields in the ontology are more strongly typed than others. So things like sepal role type are enumerated in the schema as well. Something else like detection type, which might be isn't. And so it does actually kind of create a little bit more work. If this is sort of, again, it's sort of a framework rather than a strict, this is what is expected. One thing that I think is actually presenting a bit of a challenge is, the current practice of the schema is to only allow a single unit type per schema. And if you're trying to build, software that converts between one output to another, this actually starts to sort of change the requirements of that software to structure data to actually transforming data. And I think then there's also risks of, does that then are you then fundamentally changing the data? Um, not all conversions can be done without some subtle changes. I think generally, if generally dealing with SI units, but I think this is one where it does kind of present a challenge, and I do think it's something that is worth kind of considering in these models. Also because if you are using this as we are to actually structure data that is then in a very immediate sense returned to users, you then run the risk of showing the data in a different format than they collected it as. Even though something as simple as changing from nanograms to milligrams, that is that is it better to keep it as it was reported, especially since it doesn't provide a means to record what was it originally reported in. Um, and then I think it's sometimes, the intended utilization of elements of the ASM are not self-evident. I won't get into it here, but I think we've introduced a calculated data documents to help extend the model, but there is still confusion between calculated data and process data. Technique documents versus measurement aggregate documents. Why the document and not the aggregate document is the array. So I think there are some things that um, I think there's good rationale behind these, but there's not yet enough sort of documentation out there to kind of help people who haven't been sort of steeped in this. And then ultimately, this process is inherently going to have some ambiguity. Which field is most appropriate to map this thing to? Because again, part of the exercise is to kind of get these things into a sort of a common vocabulary. But then determining, where is the model lacking in that? Should something really actually be included but isn't there, and then what is just sort of maybe superfluous that can be left behind. So then, in terms of having gotten through that, there's then the work of actually sort of writing the code to do this. And so a few things that we've adopted in the repo that have, I think, actually worked out really well. So one is we've adopted kind of a two-part architecture to all of these adapters with this sort of structure classes and parser classes, and I'll get into those a little bit more. The other thing too is that we've included a utility that will automatically generate the Python classes from the JSON schemas, and this makes the life a lot easier just in terms of the amount of sort of actual things that have to be sort of written by developers, but also when you change a schema, it's much easier to regenerate the classes. And then actually sort of using graph representations in the code to actually help handle cases where there's internal references within the JSON, or there need to be internal references within the JSON. So I think one thing for folks who don't come from a development background are aren't kind of familiar with Python classes, basically within the repo we have what we call models, which are really just class representations of the ASM JSON. So for folks who are maybe more familiar with the JSON, if you sort of look at these classes on the right, you can sort of see how they would then map to portions of the schemas. And we actually said we can generate these automatically using another open source utility called Data Model Code Gen, which is actually specifically built for kind of doing this sort of work. And I think this is one thing that also might be kind of more broadly useful to the community, as I'll get to later. And then the other thing is sort of again taking the sort of two-part approach to the way that the code works. If you actually look at the code of any of the converters, you actually see there's two scripts. There's the structure script and then the parser script. And so what the structure script does is actually then goes through and tries to sort of extract all the information into these Python classes. And so here an example is pulling the data out of Bioplex Manager into the data class for an analyte document. And Bioplex Manager is an instrument used to do XMAP assays or multi-analyte profiling assays. Then sort of the second part of this is then it's actually, we can then use the parser functions to then take these classes and write them sort of directly to the structure of the ASM. And so this actually kind of makes it easier because then you're not trying to do this all at once, and it really does sort of divide the problem in half. It's get the data out and then it's write to ASM. So yeah, so I think in terms of like some of the lessons learned here, yeah, definitely having this sort of divide and conquer approach has proved to be very, very beneficial. And I think as we sort of bring in new, contributors to it, I think it's more tractable for them to get going, so they can kind of start writing structure code before writing parsing code. And the other is that actually the Python classes themselves actually can be a more intuitive entry point for some of the developers, for folks who aren't really familiar with looking at JSON schemas, but our Python developers, it actually makes the data models clearer to them and what they're trying to do. This didn't come with sort of a free lunch, though. For folks who might look at our repo, then look at the Allotrope GitLab, you'll notice that there are some differences between the way the schemas themselves are structured. And this was actually that the utility that we're using had some trouble handling the sort of the modularized schemas that, one of for, in things like the liquid chromatography schemas. And this is something that meant that we had to kind of create more sort of fully articulated schemas. So we wouldn't actually call them truly embedded, but um, and this is something we actually are working to resolve, because I think there's a lot of value in terms of clarity, maintenance, and comparing between the two repos when the schemas follow the same pattern. Um, and so I think, getting through this, realizing the benefits, and I do want to stress that, I think just in the time that we've been working on this project, we've seen very real benefits. And so while I'm not demoing the Benchling product here, this has the having invested in this library of converters has really enabled true no code integrations into Benchling. It is now possible to, along with some of the other functionalities that we built as part of our Benchling Connect product, you can set up the ingest from complicated data files in minutes. Something that it really with kind of point and click. The other thing is that the defined structures are really helping us um, start to bring this data into other aspects of our product to kind of that are more user facing. So it's simplifying the ability to create data sets for our analysis tools, and it's also going to help us be able to write better queries into the data that's stored in Benchling. And then lastly, is what I kind of highlights in that actually we are, that is actually part of the open source project, which is actually, the ability to, but it's just an example of this, is the ability to actually kind of build tools directly off the ASM once you have predictable structures, including actually very interesting visualization. So this video is actually a utility that one of our colleagues built to to actually represent some of the elements in this. So what we're showing here is this is real qPCR data, and so you can kind of see of what this looks like. It's very big, but one thing that for folks who are familiar with qPCR is that qPCR actually has a lot of calculations that are done to sort of return the results that are necessary. So you start with crossing threshold values, but then to actually determine things like relative expression, there's actually a lot of relations that have to be done. And we've done this implementing the calculated data document in the ASM. But as you can also see, a given file, might end up being, 30,000 lines or so. So it's really not something that is, even though one of the virtues of the ASM is that it is sort of human readable, there's a limit to what is really human readable once you kind of get to a certain scale. But because all of this is kind of has a defined structure, and you can now actually start to build visualizations using these relationships, actually using a graph. And so this is actually a little bit different than what I called before. So this is now sort of doing the graph the other way. Initially, we actually were using the graph to generate these things, but now this is actually basically using a graph to represent these. And so skip ahead to where we get to the um, where we get to the output. And so this is we're basically now passing this to a utility within the library that will generate the dot file, which is the base of the graph, and then turning this into an SVG. And so now what we actually get is um, all of the relationships between the calculated data documents, although this could be sort of any internal reference in the JSON, can now be represented as a graph. And why we actually think this is sort of really powerful. One, it's a good validation tool for, are the relations between the data what we expect? But also, I think one of the goals of tools like the ASM is that it is meant to sort of document this data for people who are not practitioners of this technique. And if you are someone who doesn't know who's on, deeply familiar with the qPCR, do you know how a delta delta CT value is actually generated? However, because that's sort of a standard calculation, that can be included in the logic of the converter. It's then um, represented by the internal references in the JSON, and these can be of sort of arbitrary length. And then we can now render you can then build a visualization off of this and show you, oh, this is how that number was arrived at and what is the path. And you only to then understand the calculation, you only have to sort of follow the path. Um, so being mindful of time and knowing that it's late in the day, I will. So, I guess maybe just sort of returning to, kind of some of the comments at the top. I do sort of ask folks here, everyone who, uh, if you've taken the time to come to this conference or even join remotely, I think clearly it shows that you have an interest in this standard. And so I guess I would ask, maybe for you to help sort of continue the work of improving the standard. I think we've seen it is very valuable, but it's continuing to grow. In the sort of the last talk we saw, there were domains we haven't represented, and I think even the techniques that are represented need refinement. And so I guess I would really ask for, come to one of the working groups. This is really where the work of the standard gets done, and it really benefits from, the collective expertise of the community. I wasn't able to join the updates earlier, but I know, the recent weeks of the work that's being done on the NMR model, it's been just really interesting, and it's really very good to have a sort of diversity of opinions there. I would sort of put out a call to the Allotrope board and then the folks who are sort of a part of the foundation to sort of give some thought of how we can sort of improve the effectiveness of the working groups. I think those who have been participating lately, I think we've run into a few challenges with sort of the ontology itself that then impedes the modeling. And I think in order to sort of build these models quickly and implement them, I know we want to get it right, but often sometimes I feel like we end up sort of churning on these. And so I know, I've been leading the flow cytometry working group, and I think as we've tried to sort of, as that part of that working group, implement sort of a process by which we're going to sort of make decisions and move forward. And I would sort of maybe like to see something like that adopted in some of the other working groups as well. And then, sort of a call to, help implement this standard. You said this is an open source project. So, in again, non-code contributions are more than welcome. Try the converters on your own data. If they don't work, post an issue. Review the requirements that we wrote. If you're familiar with these instruments and their output, see if you sort of agree with the mapping that was done. Submit files for either, that can be used for test coverage for the existing adapters, or ones that you want to see. Something that actually can sometimes be a blocker on developing new ones is actually having enough of that sample data, as I referred to earlier, to know that we have confidence in what we're building will sort of do the job. And then, of course, if you are a developer and are interested, please review the code and consider contributing a new converter. So with that, and I think I kept it on time, I'm happy to take any questions.
Thank you, Joe.